There's a monster sitting at the center of our galaxy, and for decades, we've only seen its shadow. Sagittarius A, a black hole about 4 million times the mass of the Sun, 26,000 light-years away, has been hiding behind the wall of dust so thick our best telescopes could barely scratch the surface. Then the James Webb Space Telescope finally turned its infrared eyes straight into that darkness. In this video, we're going to follow Webb right into the core of the Milky Way, past the dust, into the crowded star fields, and down toward the last light year around the black hole itself. What it saw there forced astronomers to rewrite what they thought was happening in our galaxy's heart. But before we continue, please subscribe to the channel to give your support. Let's continue. How do you deal with a 4 million solar mass object that sits in the dark, right at the center of your own galaxy, and refuses to show itself in ordinary light? At about 26,000 light-years from where you are, in the direction of the constellation Sagittarius, there's a compact object we call Sagittarius A. Its mass is about 4.1 million times the mass of the Sun, all packed into a region smaller than our solar system. We know that not because we see the object itself, but because we see what it does to the stars around it. One of those stars is called S2. It orbits Sagittarius A on a very stretched, elongated path, and at closest approach, it moves at around 7,650 kilometers per second, which is about 4,750 miles per second. That is more than 2% of the speed of light. A star does not reach that speed unless something extremely massive is pulling on it in a very small volume of space. When astronomers measure S2 and similar stars, track their orbits, and apply gravity, they get the same answer over and over. There is a supermassive black hole at the center of the Milky Way. So the basic mass and the basic location are not a mystery anymore. The real problem has been something else. If this object is so dominant, why has it been so hard to actually see its environment in a clear way? If you look toward the Galactic Center in visible light, the kind your eyes and a normal optical telescope use, you mostly see a crowded star field that fades into a dark band. Between you and Sagittarius A, there are about 8.2 kiloparsecs of interstellar gas and dust. That is roughly those same 26,000 light-years of material along the line of sight. The dust grains are very efficient at blocking visible light. Astronomers describe this with extinction, and toward the center, it is more than 30 magnitudes in the optical. You do not need to remember the number, only the consequence. Almost all visible light from the central region is absorbed or scattered away before it gets here. That means that in ordinary light, the Milky Way's core is basically hidden. For decades, the best you could do was switch to longer wavelengths, into the infrared. Infrared light, especially at a few micrometers and beyond, is less affected by dust. The Hubble Space Telescope, when used with its near-infrared instruments, could already see deeper into the central bulge. The Spitzer Space Telescope, designed for infrared, gave even more detail on warm dust and cooler stars near the center. But both had limits. Their mirrors were smaller, their detectors were less sensitive, and from low Earth orbit or Earth-trailing orbits, they had to deal with more thermal noise. So even with Hubble and Spitzer, the inner few light-years around Sagittarius A, what astronomers call the central parsec, still looked like a blurry pileup. Stars overlapped, gas and dust blended together, and the spatial resolution was simply not enough to separate fine structures. You knew there were disks of gas, cavities, filaments, and maybe shocks near the black hole, but you cannot map them cleanly. At that point, the obvious need was a telescope that could combine three things at once: very sharp angular resolution, extreme sensitivity, and strong performance in the near and mid-infrared, where dust becomes more transparent. That combination is exactly what James Webb Space Telescope was designed to deliver. Webb's primary mirror is 6.5 meters across, about 21 feet, made of 18 hexagonal beryllium segments that act together like a single large mirror. It operates not in low Earth orbit, but around a point called the second Lagrange point, L2, about 1.5 million kilometers from Earth, roughly a million miles away. Out there, behind the multi-layer sun shield, the telescope can cool down to around 40 Kelvin, around minus 233 degrees Celsius, or about minus 387 degrees Fahrenheit. That cold environment keeps its own infrared glow extremely low, which is critical if you want to detect faint infrared light from distant, dusty regions. On top of that, you have the instruments. NIRCam, the near-infrared camera, covers roughly 0.6 to 5 micrometers in wavelength. MIRI, the mid-infrared instrument, covers roughly 5 to 28 micrometers. In those bands, a lot of the dust toward the galactic center becomes semi-transparent, and the dust itself starts to glow because it's warmed by stars and other energy sources. With its large mirror and precise optics, Webb can resolve details at the galactic center down to scales of a few hundred astronomical units. One astronomical unit is the Earth-Sun distance, about 150 million kilometers, around 93 million miles. So we're talking about structures a few hundred times that size, mapped at 26,000 light-years away. So you might say, problem solved. Webb points at Sagittarius A, takes a picture, and we finally see the black hole itself. But there's another piece of the story, one you probably remember. We already have a direct image of the region right next to the event horizon. In 2022, the Event Horizon Telescope, a global array of radio observatories acting like one Earth-sized dish, released the first radio image of Sagittarius A. That image shows a glowing ring about 51.8 micro-arcseconds across. If you convert that to a physical size at the distance of the galactic center, you get a ring about 51.8 million kilometers across, roughly 32 million miles, or about 37 times the diameter of the Sun. That ring corresponds to the region where light orbits the black hole, before some of it falls in and some of it escapes. It was a huge confirmation of general relativity and of the black hole interpretation. However, that Event Horizon Telescope image has important limitations. It's made in radio waves, not in infrared or visible, so it traces synchrotron emission from hot electrons in the innermost accretion flow, not the cooler gas and dust farther out. It's also time-averaged because Sagittarius A changes brightness on timescales of minutes, and the observations had to be combined over hours to reconstruct a single stable image. And it gives you almost no information about the larger environment, the clouds, the stars, and the multi-phase gas that actually feed and react to the black hole. This is where Webb doesn't compete with the Event Horizon Telescope. It fills in the rest of the picture. Webb can't resolve the event horizon itself, its angular resolution isn't high enough for that, but it can map everything from a few thousand astronomical units outward, the region where gas is falling in, being shredded, heated, and sometimes blown back out. It can show you where star formation is happening near the center, where molecular clouds are being compressed or eroded, and how the chemistry of the gas changes as you move closer to Sagittarius A. So the role of Webb here is not to redraw the famous ring, it is to explain what kind of environment produces that ring in the first place. Think about it as finally seeing the entire neighborhood, not just a single building. You get to see the fuel supply, the traffic patterns, and the damage left behind by past outbursts. In this story, that means starting far out and working our way in with Webb as our guide. You will see huge molecular clouds like Sagittarius B2, with millions of solar masses of gas, where Webb's mid-infrared vision reveals dense clumps, warm dust, and complex molecules. You will see regions like Sagittarius C, closer to the center, where Webb's near-infrared images break the area into individual young stars, jets, and shocks. And then, in the last step, you will see the central parsec itself, the inner few light years around Sagittarius A, where Webb's spectrometers show multiple gas phases, sharp fronts where energy is being dumped into the surroundings, and a chemical pattern that says recent violent history. All of that together is why scientists were not just pleased, but genuinely surprised. Some of the patterns Webb reveals in the galactic center do not match the simple expectation that more gas automatically gives you more stars, or that our black hole has always been as quiet as it is today. But there is still a basic question we need to answer before we dive into those details. If Webb is so powerful and the galactic center is now in reach, what exactly makes this region such a difficult, almost hostile target for telescopes? And why did it take us so long to get this clear a view at all? How do you study the most important region in the whole galaxy when almost all of its light is blocked before it reaches you? Sagittarius A sits about 8.2 kiloparsecs from us. That's around 26,000 light-years, straight through the disk of the Milky Way. Along that entire line of sight, there is gas and, more importantly, dust. Not the big dust you wipe off a table, but tiny grains of carbon and silicates floating between the stars. For visible light, the kind your eyes use, those grains are brutal. They absorb and scatter photons so effectively that astronomers say the extinction toward the galactic center in visible wavelengths is more than 30 magnitudes. In simple terms, that means the light is dimmed by a factor of 1,000,000,000 times 1,000,000,000. The original signal is basically erased. So when you point a normal optical telescope toward the center, what you get is a kind of dark lane with some stars around it, and almost none of the true core shows up. In human terms, trying to see the center of the galaxy in visible light is like trying to spot a single candle on the other side of a continent-wide sandstorm. The light exists, but the particles in between scatter it in every direction, and almost nothing comes straight to you. That is the first big barrier. Even before you worry about black holes or exotic physics, you're looking through 8.2 kiloparsecs of fog. So if visible light is basically useless there, what kind of light can actually get through that fog and still tell you something real about the galactic center? The answer is you shift to longer wavelength, into the infrared. Infrared photons, especially those with wavelengths of a few microns and longer, interact differently with dust grains. Because their wavelength is closer to or larger than the size of the dust grains, they scatter less and are absorbed less. That means a much higher fraction of those photons make it all the way to your telescope. This is where Webb's instruments matter. NIRCam, the near-infrared camera, covers roughly 0.6 to 5 micrometers, which overlaps with the longest wavelengths Hubble could see, but with far better sensitivity and resolution. MIRI, the mid-infrared instrument, stretches from about 5 to 28 micrometers, deep into the regime where dust not only lets light through, but also glows because it has been warmed by stars and shocks. In these bands, a region that looked like a dark smear in visible light suddenly becomes crowded, full of individual stars, arcs of gas, filaments, and sharp edges where shocks are heating material. So infrared solves the wall of dust problem, at least partly. But once you can see through the fog, you run into the second problem. The galactic center is insanely crowded. The inner parsec around Sagittarius A, which is only about 3.26 light-years across, contains over 1,000,000 stars. The average separation between stars in that zone can be around 0.01 parsecs or less. That's only a few thousand astronomical units. Compare that to the solar neighborhood, where the nearest star to the Sun, Proxima Centauri, is about 1.3 parsecs away, more than 4 light-years. Near Sagittarius A, stars are crammed together in a way that is completely outside your everyday experience. If you live near the center, your night sky wouldn't have a few thousand stars visible to the eye. It would have hundreds or thousands times more, packed into every patch of sky. It would look less like a calm, dark background with dots, and more like standing in the middle of a city center at night with bright points in every direction. For astronomers, this is a serious technical problem, because on the detector, the light from many stars and gas clouds lands on the same pixels. If your telescope's resolution isn't high enough, all those separate objects blur into each other, and you can't tell which light belongs to which source. Webb's large mirror gives it very sharp angular resolution in the infrared, so it can split this crowded city center into more individual sources than any previous infrared telescope. But even with that, the central parsec is close to the limit of what any current instrument can de-blend cleanly. You're fighting against dust and against extreme crowding at the same time. And then there's a third complication. Even if you could freeze the scene and sort every star and cloud, Sagittarius A itself refuses to stay quiet. It flickers and flares. In radio and infrared, Sagittarius A is a variable source. Its brightness can jump by factors of 10 to 100 on timescales of minutes to hours. That's because the gas very close to the event horizon is turbulent, magnetized, and moving at a large fraction of the speed of light, so small changes in the flow can produce big changes in radiation output. When the Event Horizon Telescope made its image of the ring, the team had to fight this variability because the brightness pattern changed while they were collecting data. They had to average over time to reconstruct a stable ring, and even then, the details are tricky to interpret. For Webb, this variability means you cannot just take a random snapshot and assume it represents some calm, steady state. You need to plan. Observations of the Galactic Center with Webb are often coordinated with ground-based infrared telescopes and with X-ray observatories. When Sagittarius A goes into a flare, they want to see it in multiple wavelengths at once to understand where the energy is coming from and how it propagates outward. That requires precise timing, careful scheduling, and sometimes a bit of luck because the flares are not perfectly predictable. So at this point, you have three serious problems stacked on top of each other: a dust wall that kills visible light, extreme crowding that blends sources together, and a central engine that changes on minute timescales. But there is still one more layer that makes the Galactic Center hard. The gas and dust are not in a single simple state. They form a mix of very different phases. Around Sagittarius A, especially in the central parsec, the interstellar medium is not uniform. There is cold molecular gas at tens to a few hundred Kelvin that forms dense clumps and filaments. There is warm ionized gas at around 10,000 to 60,000 Kelvin that produces strong emission lines. There is even hotter coronal gas at temperatures above 100,000 Kelvin that emits in very specific, highly ionized lines. On top of that, there is a smaller amount of neutral gas. Each of these phases responds differently to gravity, radiation, shocks, and magnetic fields. If you only take a simple image, all their light is added together, and you cannot tell which pixel is dominated by which phase. So the real question becomes, how do you beat all of these obstacles at once? The dust, the crowding, the variability, and the mixed gas phases, and turn the Galactic Center from a confusing blur into a physical, understandable system. This is where Webb is uniquely suited. First, the 6.5-meter mirror gives high angular resolution in the infrared, sharp enough to separate many individual stars and small gas structures even in the core. Second, its sensitivity is huge, so it can pick up faint emission from different gas phases, not just the brightest sources. Third, and this is crucial, its instruments can do spectroscopy across the mid-infrared. In particular, MIRI's medium-resolution spectrometer can take a field around the Galactic Center, and instead of giving you just one image, it gives you a three-dimensional data cube. 2 dimensions on the sky, and 1 dimension in wavelength, from about 5 to 27 micrometers. Inside that data cube, every point in the image has a full spectrum. Different gas phases have different spectral fingerprints, specific emission lines from molecules, from ionized atoms, and from highly ionized coronal species. By looking at which lines are strong in which locations, astronomers can decompose the zoo of gas phases. Separate where the molecular gas dominates, where the warm ionized gas dominates, and where the hottest coronal gas shows up. On top of that, tiny shifts in the wavelengths of those lines due to the Doppler effect reveal motions of tens to hundreds of kilometers per second, giving you not only a map of what is where, but also how it is moving. Put all of this together, and Webb turns the Galactic Center from a single, messy picture into a detailed 3D map in space, wavelength, and velocity. That is why once the first Webb data started coming in, the field shifted very quickly from "we know there is a black hole there" to "we can now trace how gas flows, where stars are forming, and how recent explosions and outflows have reshaped the core." Now that you see why the Galactic Center has been such a difficult target, and why Webb finally has the right tools to crack it open, The next step is to look at the biggest reservoirs of gas that could one day feed Sagittarius A, starting with one of the most extreme molecular clouds in the whole galaxy, Sagittarius B2. How do you get a calm, quiet-looking black hole at the center of the galaxy when just a little farther out you have one of the most extreme gas reservoirs the Milky Way has ever built? Near the Galactic Center, a few hundred light-years from Sagittarius A, there is a beast of a molecular cloud called Sagittarius B2, usually shortened to Sgr B2. This thing is not a normal cloud. It contains somewhere between about 3 and 10 million times the mass of the Sun in gas alone. In size, it stretches roughly 150 light-years across, so around 1.4 trillion kilometers, about 870 billion miles. When astronomers say giant molecular cloud, this is one of the benchmark examples. To give that some context, you can think of all the cold molecular clouds in a small galaxy, the places where stars form. Now, take the mass in those clouds and compress a big chunk of it into a region smaller than the distance between us and the Large Magellanic Galaxy, which sits about 160,000 light-years away. Sgr B2 is like packing an insane amount of star-forming fuel into a relatively compact volume, sitting in the inner Milky Way, not in some exotic distant galaxy, but in our own backyard by galactic standards. So here's the question. When Webb points its mid-infrared eyes at something that massive and that dense, what does it actually see? Does it just look like a smooth blob of gas? Or does it split apart into something more detailed and more violent? With JWST's MIRI instrument, Sgr B2 stops being a vague radio cloud and turns into a structured, glowing landscape of dust and embedded stars. In mid-infrared wavelengths, dust grains that are warmed by nearby young stars start to radiate strongly. In the processed images you usually see from MIRI, that warm dust is mapped into bright, hot colors. But the key physics is simple. Dust grains at tens to a few hundred Kelvin, so from maybe minus 250 to minus 70 degrees Celsius, or about minus 420 to minus 90 degrees Fahrenheit, are glowing in exactly the wavelengths MIRI is designed to catch. Across Sgr B2, Webb's data shows bright, intricate knots and ridges of this warm dust emission. These are regions where massive newborn stars are already shining, their radiation heating the surrounding dust. Between those bright areas, there are darker patches and lanes where even mid-infrared light has trouble getting out. Those are the densest cores, clumps of gas and dust that are so thick that photons at 10, 20, even 25 micrometers are being absorbed or scattered. In other words, even in the X-ray vision mode of mid-infrared, some parts of Sgr B2 are still basically opaque. That tells you just how extreme the densities are in the heart of this cloud. So once you see all this warm dust and hidden cores, the next obvious question is, how good is this cloud at actually turning all that gas into stars? Is it just sitting there, or is it a factory running at full power? This is where Sgr B2 breaks the usual simple rule. Even though it contains only around 10% of the total gas in the Galactic Center region, it is responsible for roughly half of the ongoing star formation there. So a small fraction of the gas is doing a huge fraction of the work. If you like a down-to-earth comparison, that is like having one city block that manufactures half the cars for an entire country. It is not just active, it is hyper-efficient. Webb's view supports this. The mid-infrared shows clusters of deeply embedded protostars, compact H2 regions where young massive stars are ionizing the gas around them, and complex structures where winds and radiation are carving cavities. You are not looking at a quiet, slowly evolving cloud. You are looking at a region where gravity has clearly won against turbulence and magnetic fields in many places, and is collapsing gas into stars at a very high rate. But here's the deeper twist. If this cloud is already exceptional in mass and in star formation efficiency, what is going on chemically inside it? Is it just simple hydrogen and helium, or is it doing something more interesting for the long-term story of planets and life? For decades, radio and millimeter telescopes have shown that Sgr B2 is one of the most molecule-rich regions known in the galaxy. Astronomers have detected a long list of molecules there, from simple ones like carbon monoxide and ammonia to more complex organics with several atoms linked together. What Webb adds with MIRI spectroscopy is a mid-infrared view of the vibrational modes of these molecules and ices. In plain language, different molecules and icy coatings on dust grains absorb and emit infrared light at specific wavelengths when their bonds stretch and bend. MIRI spectrometers can pick out those features. In Sgr B2, Webb highlights signatures from carbon-bearing species, nitrogen-bearing species, and oxygen-bearing species, including complex organic molecules and ices. You're looking at a chemical buffet full of ingredients that, in calmer environments and later stages, can end up in protoplanetary disks and eventually in comets, asteroids, and planets. So Sgr B2 is not just a huge fuel tank, it is also a prebiotic chemistry lab running close to the central black hole of the Milky Way. The environment there is harsh, with strong radiation, shocks, and high densities, but the chemistry is rich, not simple. That's important because it tells you that even in extreme parts of a galaxy, the building blocks for complex molecules can form and survive. And that raises a bigger question. If Sgr B2 is forming stars so efficiently and hosting this kind of complex chemistry, what does that mean for Sagittarius Asterix itself? Is this cloud just doing its own thing, or is it part of a larger system that ultimately feeds the black hole? On larger scales, Sgr B2 sits in what astronomers call the central molecular zone, the inner few hundred light-years of the Milky Way that are loaded with dense gas. Gravity, galactic rotation, and bar dynamics in the Milky Way's disk can funnel gas inward over millions of years. Clouds like Sgr B2 form in that environment, collapse, and turn some of their gas into stars. But not all of the gas gets locked up in stars. Some of it is stripped, blown out by stellar winds and supernovae explosions, or torqued further inward by the galaxy's gravitational potential. From Webb's perspective, Sgr B2 is part of the outer suburbs of the Galactic Center. It's far from the event horizon in absolute terms, hundreds of light years away, but in the context of the Milky Way's full size, it's already near downtown. The stars forming there will evolve, explode, and push gas closer to the central tens of light years. Over long timescales, this process can send material inward, where other clouds and structures like the circumnuclear disk around Sagittarius Asterix can capture it and feed it even closer to the black hole. So when you look at Webb's data on Sgr B2, you're not just seeing a random cloud. You're seeing a key stage in a supply chain. Millions of solar masses of gas, intense star formation, rich chemistry, and energy feedback are all part of a pipeline that, step by step, can deliver matter towards Sagittarius Asterix. In that sense, Sgr B2 is both a star factory and a distant fuel depot for the black hole. But if Sgr B2 is the massive, obvious giant in this region, it is not the only player. Closer in, there's a more compact, more chaotic-looking zone called Sagittarius C, where Webb has found violent newborn stars driving long jets and shocks right in the inner galaxy. So the next question is, as you move closer to the center, does the star formation get calmer, or does it get even more aggressive and explosive? How do you move closer to the galactic center and have star formation get even more violent, not calmer, even though the gravity and conditions are already extreme? Closer in than Sagittarius B2, there is another, less famous, but crucial region called Sagittarius C. Sagittarius C sits nearer to the core, in an area that radio astronomers already knew was messy, with tangled gas, strong magnetic fields, and odd filamentary structures. For a long time, it was treated almost like background noise near the center. Complicated, interesting, but not the main star-forming headline. That changed when Webb's near-infrared camera, NIRCam, took a deep, high-resolution look. In NIRCam's view, Sagittarius C is no longer just a complicated gas patch. It breaks into a network of protostars, jets, and bow shocks, places where material launched from baby stars slams into the surrounding cloud at high speed. What used to look like a fuzzy region of emission turns into individual sharp arcs, knots, and filaments. You see compact young stars buried in dust, with clear signs that they are actively accreting gas and ejecting it at the same time. This is not a quiet cloud just starting to form stars. This is a region already in the middle of a burst of activity. So once you see these jets and bow shapes everywhere, the next question is, how big are these flows? Are they small local features, or are they on truly massive scales for a single forming star? Webb's data show at least two very massive protostars in Sagittarius C, driving outflows that stretch over about 1 parsec, which is roughly 3.26 light-years. That distance is about 206,000 astronomical units, so if you put the Sun at one end of that flow, it would go far beyond the orbit of Pluto, keep going, and still not be done. These flows show up as long, curved bow shocks and filaments in emission lines from hydrogen and other ions, tracing where the jets are plowing into the cloud and heating, compressing, and ionizing the gas. For a single protostar to drive a flow that long, it has had to have been launching material for a significant time and with a lot of power. The speeds involved are on the order of tens to a few hundred kilometers per second, which is tens of thousands to hundreds of thousands of kilometers per hour, much faster than any spacecraft we have built. This tells you that the forming stars here are not small, they are massive, and their feedback is already reshaping their local environment, even before they have finished forming. But if those giant flows were the only story, you might think Sagittarius C is just about a couple of especially big stars. The more important question is, what is happening on smaller scales all across the cloud? Is star formation limited to a few giants, or is it happening everywhere at different scales? On top of the large bow shocks, JWST identifies on the order of 40 smaller shock features spread throughout Sagittarius C. These smaller structures are likely powered by lower mass protostars, stars more like the Sun or a bit bigger than the Sun, scattered through the region. Each of these protostars is driving its own little jet or outflow, slamming into the surrounding gas at more modest but still significant speeds. When you add up all these features, you get a clear picture. Star formation in Sagittarius C is not a slow, isolated process. It is happening throughout the cloud, with multiple generations and mass ranges involved at the same time. So instead of a gentle drizzle of new stars, you have something closer to a full storm, with large and small outflows, shocks, and cavities all overlapping. The gas is being stirred, compressed, and shredded from many directions at once. That matters because such a turbulent environment affects how efficiently gas can collapse into new stars, and how much material can be driven inward toward the central tens of light years. At this point, there is a natural follow-up problem. If the line of sight to the Galactic Center is full of dust, and Sagittarius C is embedded in that, how do you know the true brightness and mass of the stars you are seeing? How do you avoid being fooled by dust dimming and reddening the light? This is where Webb's NIRCam data towards Sagittarius C gives something very important: the first precise infrared extinction curve to the galactic center along this particular sightline. An extinction curve is basically a rulebook that tells you how much starlight is being dimmed at each wavelength by dust, and how the color of the light is shifted. By looking at large samples of stars with known or predictable intrinsic colors and measuring how their observed colors differ, astronomers can derive how dust affects light at different infrared wavelengths. In Sagittarius C, Webb's sensitivity and resolution let astronomers build a detailed curve for the near-infrared, instead of having to rely on rough, average estimates. With that in hand, you can correct the observed brightness of stars for dust effects more accurately, which means you can turn apparent brightness into true luminosity and then into reliable mass estimates. Without a good extinction curve, every measurement of how massive a star is or how strong an emission region is off by an unknown factor. Near the galactic center, that would mean your whole picture of the energy budget is skewed. With Webb's extinction curve, the calibration improves and the physical interpretation becomes much more solid. So now you know that Sagittarius C is both chemically and dynamically complex, loaded with protostars of different masses, driving outflows on scales from thousands to hundreds of thousands of astronomical units, and you have the tools to measure their true properties. The next step is to ask, how does this fit into the bigger story with Sagittarius B2 and the central black hole? Is this just another isolated hotspot, or part of a larger pattern that explains how the inner galaxy evolves? Seen together, Sagittarius B2 and Sagittarius C send a clear message about the central few hundred light-years of the Milky Way. This region is not dead, and it is not gently winding down. It is actively and violently forming stars in multiple clouds with high efficiencies. The massive stars being born in these places will live short lives, maybe a few million years, and then explode as core collapse supernovae. When they do, they will inject huge amounts of energy and heavy elements into the surrounding gas. That enriched, energized gas doesn't just stay where it is. Some of it will be blown outward, some will be mixed sideways, and some will be driven inward by gravity, bar dynamics, and the overall potential well of the galactic center. In that sense, Sagittarius B2 and Sagittarius C are parts of a star-forming conveyor belt. They take gas funneled into the central molecular zone, convert a fraction into stars, and then send metal-rich, stirred-up material closer to the central tens of light-years, where Sagittarius A sits. Over long timescales, this conveyor belt shapes what kind of gas reaches the immediate environment of the black hole, what its chemical makeup is, how turbulent it is, and how likely it is to feed the black hole efficiently. Webb's view of Sagittarius C locks in one key part of that system. It shows you that even very close to the center, star formation is not suppressed, it is intense and disruptive. So the natural follow-up question is, if the clouds in the outer and middle parts of the central molecular zone are this active, what happens when you finally step all the way into the last light year around Sagittarius A itself? Does the environment stay this chaotic, or does the physics change again once you're right on the edge of the black hole's direct influence? How do you really know what is happening in the last light year around a black hole, when you can't see the event horizon, but you can see everything the black hole is doing to its surroundings? Right around Sagittarius A, inside roughly the central parsec, about 3.26 light-years across, Webb's mid-infrared mission goes into a different mode. It stops being just a camera. It becomes a full mapping machine. In its medium-resolution spectrometer, MRS, MIRI doesn't just take one picture. It scans the area and gives you thousands of tiny spatial pixels, and for each of those pixels, it records a full spectrum from about 5 to 27 micrometers. So instead of a flat image, you get what astronomers call a data cube. 2 dimensions on the sky, and the third dimension is wavelength. For you, the key point is this. Every little patch near the black hole, every filament, every bright knot, isn't just a dot of light. It comes with a detailed fingerprint, telling you what elements are there, what ionization state they're in, how hot the gas is, and even how fast it's moving along the line of sight. When you stack all those spectra together, you no longer are guessing what the gas is made of, or where the hot regions are. You can map them directly, pixel by pixel, across the whole central parsec. So once you have this 3D cube, the next step is obvious. You ask, how many different kinds of gas are you actually dealing with? Is it one uniform soup, or a mixture of very different phases that all overlap in the same region? To answer that, Astronomers feed these spectra into models using a photoionization and plasma code called cloudy. That code takes in things like radiation fields, gas densities, and chemical abundances, and predicts what the emitted spectrum should look like for different gas phases. By matching the predicted lines to what Webb actually sees, they can break the environment into distinct components. For the region near Sagittarius A, the modeling says there are four dominant phases. First, there is warm ionized gas, with temperatures around 10,000 to nearly 60,000 Kelvin. That is gas where atoms have lost one or more electrons, and it produces strong emission lines in the mid-infrared from species like ionized neon, sulfur, and others. Second, there is molecular gas, much cooler at tens to a few hundred Kelvin, where hydrogen is in molecular form and more complex molecules can exist. Third, there is coronal gas, hotter than 100,000 Kelvin, where atoms are stripped of many electrons, and you see so-called coronal lines from highly ionized species. Finally, there is a smaller neutral component, gas that is not fully ionized, sitting between the cold molecular and the warm ionized phases. Each of these phases leaves a different pattern in the spectrum. The warm ionized gas shows strong forbidden lines at specific mid-IR wavelengths. The molecular gas gives you rotational and vibrational lines, plus features linked to dust and ices. The coronal gas lights up at particular high ionization lines, and the neutral gas shows weaker, subtler features. Webb, with the MIRI MRS data cube, sees all of these at once, and the modeling lets you disentangle how much of each phase is present at each location. So with that breakdown in hand, the natural question is, which of these phases is actually dominating what you see? Where is most of the mid-infrared emission really coming from? Is it the cold, dense molecular gas, or something else? Near Sagittarius A, there are two key structures people talk about. One is the circumnuclear disk, the CND, a ring-like arrangement of molecular gas and dust that orbits the black hole at distances of a few parsecs. The other is the central cavity, the CC, the innermost region inside that ring, much closer to the black hole. You might expect that because the CND has a lot of dense molecular gas, it would dominate the emission. But Webb's analysis shows something different. When you integrate the spectra over the CND and over the central cavity, you find that most of the mid-infrared emission actually comes from the warm ionized gas, not from the molecular component. The molecular gas in the circumnuclear disk is clumpy, broken into dense knots and filaments, and it does emit, but the smoother, more extended warm ionized phase produces a larger share of the light that Webb sees. Inside the central cavity, the molecular gas almost disappears, which fits what you'd expect near a black hole bathed in harsh radiation and hit by intense stellar winds. Close in, molecules are easily destroyed, dust is eroded, and the gas is kept hot and ionized. So the picture you get is a clumpy ring of molecular material at a few parsecs with pockets where star formation and dense gas survive, wrapped around an inner zone where warm ionized gas fills much of the volume and molecular gas is scarce. On top of that sits the coronal gas, hotter and more rarefied, marking the most energetic regions. That already tells you this is not a calm disk slowly and quietly feeding a black hole. It's a multi-phase, dynamically heated environment. But what about the actual chemical mix of this gas? Is the central parsec made of old material that's been sitting there for billions of years? Or does Webb see signs of recent, violent processing by short-lived massive stars? From MIRI spectra, astronomers can estimate relative abundances of different elements. In the central parsec, they see that elements like carbon, nitrogen, and oxygen, the so-called CNO group, are enhanced. They also see strong signatures from alpha elements like oxygen, neon, and magnesium, which are typically produced in core collapse supernovae, the explosions of massive stars, maybe 10 to 50 times the mass of the Sun. At the same time, iron appears relatively suppressed compared to these elements. That combination is a big clue. Core collapse supernovae, which happen when massive stars die after a few million years, eject a lot of alpha elements and CNO material. Type 1a supernovae, which come from older, lower mass systems, tend to produce more iron peak elements. So if you see a pattern of enhanced alpha elements and CNO, but not much extra iron, it tells you that the gas has been enriched mainly by recent generations of massive stars, not by a huge contribution of old, iron-rich Type 1a explosions. In plain language, Webb is saying the central parsec has been polluted recently by short-lived massive stars. This is a chemically young core. It is not just a relic from the early days of the galaxy, sitting there unchanged. It has gone through relatively recent star formation with massive stars pumping out metals and energy, and then blowing up as supernovae, reshaping the composition of the gas we see today. So you now know the gas is multi-phase and chemically young, but there is another key piece. How is the energy from both the stars and the black hole actually being pumped into this medium? Where are the real battle lines between hot and cold gas? In the MIRI data, the hottest coronal gas often appears at the interfaces between molecular regions and zones dominated by warm ionized gas. These interface regions trace shock fronts, where fast winds, outflows, and possibly weak jets from near Sagittarius A are slamming into cooler, denser material. When that happens, the gas is heated to very high temperatures. Atoms are stripped of many electrons, and you get those characteristic high ionization lines that only coronal gas can produce. In other words, Webb is not just seeing static phases sitting next to each other. It's catching the boundaries where one phase is being transformed into another by energy injection. You see cold or molecular gas get hit, you see it heat up, ionize, and in some cases get blown apart. These shock fronts are literally the footprints of how power from the black hole and from massive stars propagates through the central parsec, carving out cavities, compressing some regions, and emptying others. So when you step back and look at the full picture that Webb gives you for the inner few light years, you're looking at a structured, chemically young, shock-shaped ecosystem sitting right around the supermassive black hole that, today, looks relatively faint. And that sets up a tough but important question. How do you connect a tiny glowing ring the size of a solar system to chaotic clouds stretching light years across, and say with a straight face that it's all one system driven by the same black hole? The Event Horizon Telescope gives you the innermost piece. Using radio dishes spread across Earth and acting like one planet-sized antenna, it resolved a ring around Sagittarius A about 51.8 micro-arcseconds across. At a distance of about 26,000 light-years, that angle corresponds to a ring roughly 51.8 million kilometers wide, about 32 million miles. The radius is around 26 million kilometers, which is about 0.17 astronomical units, less than half the distance from Earth to the Sun. That ring traces the photon orbit, the region where light itself is forced into nearly circular paths by the black hole's gravity. Webb cannot see that ring. Its resolution in the infrared is excellent, but not that extreme. Angularly, it tops out at a few tens of milli-arcseconds, not micro-arcseconds. What Webb does instead is pick up everything from a few thousand astronomical units outward. That is the feeding and feedback zone, the region where gas flows in from the circumnuclear disk, where stars are blowing winds and exploding, and where outflows from very close to the event horizon push back against that inflowing material. So you have two completely different tools. The Event Horizon Telescope maps the last orbit of light. Webb maps the environment that sets up what falls in and what gets thrown out. So the natural problem is, can you really say the same physics links these two layers? Or are you just putting two separate pictures next to each other and hoping they connect? A big clue comes from newer Event Horizon Telescope data, where they don't just look at brightness, but at polarization, which tells you about magnetic fields. Those polarimetric images show strong, ordered magnetic fields spiraling around the event horizon of Sagittarius A, in a pattern similar to what has been seen at the gigantic black hole in M87. That means the innermost accretion flow is not a messy, random tangle of fields. It has structure, with field lines that can guide and column outflows or jets. Those outflows do not stop at a few tens of millions of kilometers. They carry energy and momentum outward into the same gas that Webb sees on scales of thousands to millions of astronomical units. So when MIRI picks up coronal gas and shock fronts at the interfaces between warm, ionized, and molecular regions, it is very likely seeing the downstream effects of those magnetically controlled outflows and winds. Near the black hole, the Event Horizon Telescope sees the fields. Farther out, Webb sees what those fields and the associated flows are doing to the gas. But to really be sure these are not just coincidences, you need to watch the system change in real time across multiple wavelengths. That's where coordinated flare observations come in. Sagittarius A brightens in infrared and X-rays during flares that last tens of minutes to a few hours. These flares are thought to come from hotspots or sudden changes in the innermost accretion flow, maybe blobs of plasma orbiting very close to the event horizon, or magnetic reconnection events that accelerate particles. When astronomers know a flare is happening, they try to get everyone on target at once: the Event Horizon Telescope and radio, X-ray observatories like Chandra, and James Webb Space Telescope in the infrared. With that coordination, you can track how a packet of energy moves. First, you see a change in radio near the ring, then an infrared flare from hot electrons, then X-rays when the highest energy particles shine. If some of that energy propagates outward, you can later see responses in the surrounding gas, changes in mid-infrared line strengths, or heating in certain regions. It is a bit like watching a lightning discharge, not just with your eyes, but also with radio receivers and X-ray detectors, and seeing how the signal moves from the channel in the cloud to the wider environment. So with an inner ring, polarization maps, and flare timing in hand, the next real test is this: can you use all these data at once to rule out certain ideas for how the black hole is feeding and how powerful its outflows are? Accretion flow models, the mathematical descriptions of how gas spirals in and heats up around the black hole, come in different flavors. Some are very radiatively efficient, converting a large fraction of the falling gas energy into light. Others are radiatively inefficient, dumping more energy into hot, low-density gas and outflows instead of radiation. Each model predicts a different brightness and size for the ring, different polarization structure, and different levels of energy dumped into the environment. The EHT ring size and brightness already cut down the range of allowed models. Now, Webb adds another layer of constraints. The densities, temperatures, and ionization states of the gas in the circumnuclear disk and central cavity, as measured by MIRI and NIRCam, tell you how much energy is actually being deposited into that gas over time. If the accretion flow were too bright or too powerful, the surrounding gas would be hotter, more ionized, and show different line ratios than what Webb sees. If it were too weak, you would not be able to explain the presence of coronal gas and certain shock signatures. When theorists combine the EHT ring data with Webb's environmental map, they can start ruling out models whose predicted feedback does not match the observed gas phases. Some extreme jet models overshoot the observed energy in the surroundings. Some weak, low feedback models cannot account for the coronal lines and shocks. What survives is a narrower class of scenarios where Sagittarius A is in a low luminosity, radiatively inefficient state today, but still capable of launching outflows that sculpt the central parsec. So what you get is not just a pretty picture plus a cool spectrum. You get a physical link from the ring where light barely escapes out through magnetic fields and flares into the multi-phase gas that Webb dissects. And that brings you to the real payoff. Webb does not replace the famous black hole photo from the Event Horizon Telescope. It explains it. The ring tells you there's a 4 million solar mass black hole sitting at the center, bending light on scales of tens of millions of kilometers. Webb tells you what kind of gas that black hole has, how that gas is structured, how recently massive stars have exploded nearby, and how outflows are punching holes and creating shock fronts in the central parsec. Together, they turn Sagittarius A from a single icon into a whole ecosystem. You also start to see that this ecosystem is not static. The chemical youth of the gas, the presence of coronal phases, the evidence for strong but not extreme feedback all hint that the activity level of the galactic center has changed over time. There have been periods when the black hole and nearby stars dumped far more energy into the environment, and quieter periods like today. So that raises a deeper question you can't dodge. If the gas right next to the black hole is that complex and that energized, why is the star formation in the immediate surroundings of Sagittarius A so strangely weak compared to how much gas is available? And what does Webb's view say about that apparent mismatch? How can the same galactic center look like a violent storm and at the very same time behave like a dead zone for making new stars? Farther out, in clouds like Sagittarius B2 and Sagittarius C, Webb shows you a maelstrom. You have millions of solar masses of gas, dense clumps, jets, bow shocks, embedded clusters, and clear signs that stars are forming fast. That is the outer and middle part of the central molecular zone, the inner few hundred light years of the Milky Way. But when you move right in to the inner few light years around Sagittarius A, the story changes in a way that feels wrong at first. You would expect that if you pile a lot of gas into the central region, you should get a lot of new stars. More fuel, more star formation. Simple. But observations say no. Inside the central parsec and in the immediate surroundings of Sagittarius A, star formation is strangely sluggish. There's gas, there's dust, there's energy, but the rate at which that gas turns into new stars is lower than you would predict just from the gas mass. It's like seeing a factory full of raw material and machines, but most of the production lines are idle. So the question becomes, is this really a dead zone, or are we just missing the action because it's hidden by dust or too faint to see in one wavelength? This is where Webb's dual view matters. NIRCam in the near infrared is very good at picking out hot young stars, especially those that have already cleared out much of their immediate dust cocoon. MIRI in the mid-infrared is sensitive to warm dust and to deeply embedded protostars that are still wrapped in thick envelopes of gas and dust. Put those together across the inner few hundred light years, and you get a map of where stars are forming in different stages. In the outer parts of the central molecular zone, NIRCam sees many young, massive stars, and MIRI sees strong emission from warm dust and embedded sources. That matches the picture from Sagittarius B2 and Sagittarius C, active star formation. But as you track inward, closer to the central parsec, both the obvious young clusters and the deeply embedded protostars drop off. Webb still sees gas and dust there. MIRI spectra still show strong emission from warm ionized gas, but the number of clear protostellar sources is small compared to the amount of available gas. The environment right around Sagittarius A is underperforming, given how much raw material it has. So what is stopping the gas from collapsing into new stars when the ingredients are right there? One major suspect is the extreme dynamics. In the central parsec, gas is not just sitting quietly. It orbits the black hole at speeds of hundreds of kilometers per second, hundreds of thousands of kilometers per hour. That fast orbital motion means strong tidal forces. If a gas clump tries to collapse under its own gravity, the differential pull from Sagittarius A can stretch and shear it. If the clump is not dense enough, the tidal shear simply tears it apart before it can form a star. On top of that, the gas is turbulent. Different streams and filaments intersect with varying velocities, stirring the medium. Turbulence acts like extra pressure. It supports the cloud against collapse. Strong magnetic fields thread the gas as well, and those fields can also hold up material, resisting the squeeze of gravity. All of this makes it much harder for gravity to win. The gas has to reach higher densities to overcome the combination of tidal forces, turbulence, and magnetic support. Webb's measurements of gas phases and densities in the central parsec let astronomers estimate just how strong that support is. By looking at line ratios in the mid-infrared, they can infer densities, temperatures, and ionization levels in different regions. When you plug those into models, you see that a lot of the gas is warm, ionized and relatively diffuse compared to classic star-forming cores. It's not that there is no dense gas at all, but the fraction of gas in the right state for collapse is lower than you would think from the total mass alone. Even if some clumps manage to get dense enough, they face another obstacle: feedback from massive stars and from the black hole itself. The central parsec hosts massive stars that formed in the recent past. These stars pour out ultraviolet radiation and drive strong stellar winds, streams of particles moving at hundreds to thousands of kilometers per second. Some of them have already exploded as supernovae in the last few million years, dumping huge amounts of energy into the gas. On top of that, Sagittarius A, even in its current low state, emits radiation and launches outflows that interact with the surrounding material. All of this feedback heats the gas and drives shocks through it. Webb sees it directly. The warm ionized phase dominates the mid-infrared emission in both the circumnuclear disk and the central cavity. That warm gas at around 10,000 to tens of thousands of Kelvin cools more slowly than cold molecular gas. If most of the volume around Sagittarius A is filled with this warm ionized phase, the gas has a harder time cooling, condensing, and fragmenting into dense cores. It's kept in a state where gravity has less leverage. So you end up with a situation where the gas is present but stirred, stretched, heated, and ionized. Gravity still works, but it is constantly fighting against tides, turbulence, magnetic fields, and feedback. The net result is that star formation inside the last few light years is inefficient, not because the galaxy forgot how to form stars, but because the environment right next to the black hole is actively hostile to the process. For theorists, this is a real challenge to the simple picture that more gas automatically means more stars. The standard intuition in galaxy evolution has been that if you increase the gas surface density, the star formation rate should go up in a predictable way. On average, across many galaxies, that holds, but Webb's data around Sagittarius A show that locally, the relationship can break down badly. You can have a lot of gas, but if it is too stirred, too magnetized, or too irradiated, star formation can stall. That's not just a detail about our own galactic center. It feeds back into how we think about galaxies with active nuclei and starbursts. Supermassive black holes do not just sit at the bottom of the potential well and eat whatever falls in. They can also regulate their own fuel supply and the star formation around them by changing the physical state of the gas. The Milky Way center is giving you a nearby, high-resolution example of that feedback in action. So now you have two extremes sitting practically on top of each other. A few hundred light years out, clouds like Sagittarius B2 and Sagittarius C are turning gas into stars at high efficiency. Right around Sagittarius A, within a few light years, gas struggles to form stars at all. Webb is what lets you see both regimes at once, with the same instruments and the same physical diagnostics. That naturally leads to a more global question. If the core is chemically young, energetically active, but star formation sluggish, what does that say about the long-term history of the galactic center? And how do we know that recent generations of massive stars have already reshaped the composition and energy budget there in a way that goes far beyond just local star counts? How do you know the galactic center has been through a recent violent phase, even if right now the black hole looks quiet and star formation seems sluggish right next to it? The answer is in the chemistry and the actual mix of elements that Webb sees in the gas around Sagittarius A. When you look at the mid-infrared spectra from Miri in the central parsec, one of the first things that stands out is the strength of lines from ionized alpha elements, things like neon and sulfur compared to lines from iron. These aren't tiny details, they're strong, repeatable features. When you see bright emission from ionized neon and sulfur and other similar elements, and at the same time you see iron lines that are comparatively weak, that's a specific pattern. That pattern is exactly what you expect if the gas has been enriched recently by core collapse supernovae, the kind that happen when massive stars, maybe 10 to 50 times the mass of the sun, run out of nuclear fuel and blow themselves apart. Those stars live fast and die young. Their lifetimes are only a few million years, not billions. When they explode, they synthesize and eject large amounts of alpha elements and CNO elements into the surrounding gas. So when Webb picks up strong neon and sulfur relative to iron, it's basically seeing the fingerprints of those massive star deaths imprinted on the central parsec. So if core collapse explosions have left such a clear mark, you naturally ask, what about the other main type of supernova, the type 1A events, the ones that come from older, lower mass systems and produce a lot of iron? Type 1A events are different. They explode when a white dwarf in a binary system gains enough mass or merges with another white dwarf and detonates. They tend to produce a lot of iron peak elements, including iron itself and related species. Over long timescales in a galaxy, Type 1A events can significantly raise the average iron abundance in the gas. If the central parsec had been dominated for a long time by enrichment from old stars and Type 1A explosions, Webb would see strong iron lines and different element ratios. But it does not. The suppressed iron signal in the mid-infrared compared to the alpha elements says that Type 1A contributions have not dominated the recent enrichment of this gas. That does not mean there are zero Type 1A supernovae, but it does mean they have not set the main chemical pattern here. Instead, the chemical mix is tilted strongly toward what core collapse events produce. Put simply, Webb's spectra are telling you that the gas in the central parsec has been processed mainly by short-lived, massive stars that exploded relatively recently in galactic terms, not by ancient, low-mass stars that took billions of years to reach their end. This is why we say the core is chemically young. The elements you see there today remember the last few million years much more strongly than the billions that came before. Once you accept that, there is an obvious next step. If you have core collapse supernovae fingerprints everywhere, that implies there was a real burst of massive star formation near Sagittarius A not that long ago. Narratively, you can think of it like this. A few million years ago, the central parsec went through a phase where gas somehow did manage to collapse efficiently, at least in some regions, producing clusters of massive stars. Those stars lived their short lives pumping out ultraviolet radiation and driving powerful stellar winds, then ending as core collapse supernovae. Each of those stars would have dumped heavy elements and kinetic energy into the surrounding gas. Webb now arrives much later, in human terms, and measures the aftermath, the chemical ratios and the current gas temperatures and ionization states that were set by those previous events. So how much energy are we actually talking about when we say a few core collapse supernovae? It's easy to say they are powerful, but you can put real numbers on this. A single core collapse supernova releases on the order of 10 to the power of 44 joules of kinetic energy into its surroundings. If you prefer a rough comparison, that is far more energy than the sun will radiate over many thousands of years. Now imagine not one, but several of these supernovae going off within the central parsec over a period of a few million years. The combined kinetic energy they inject into the gas can rival or even exceed the total energy output that Sagittarius A produces through its current weak accretion state over the same timescale. Webb's measurements of gas temperatures and ionization states across different phases, from warm ionized gas to coronal gas, allow astronomers to estimate how much of that energy is still stored in the central parsec. Hotter gas and higher ionization levels mean more energy per particle. By fitting the spectra with models, you can get approximate energy densities, pressures, and cooling times. That gives you a handle on how much energy supernovae and stellar winds have deposited and how much the black hole has added with its own outflows and radiation. The takeaway is that Sagittarius A right now is not the only big player in the energy budget of its surroundings. Massive stars and their explosions have done and are doing a huge fraction of the work in heating, stirring, and chemically enriching the gas. The black hole and the stars are sharing control of the local environment. Once you see that, you can't treat the Milky Way center as just a simple, scaled-down version of some abstract black hole model. It becomes a concrete example of something bigger in galaxy evolution. What Webb reveals in the central parsec is basically a small-scale version of what we see on much larger scales in starburst galaxies and in galaxies hosting active quasars. In those systems, rapid bursts of star formation and powerful black hole activity happen at roughly the same time. Massive stars go through their life cycles quickly and explode, while the black hole accretes at high rates and drives outflows. Together, they reshape the gas in the inner parts of the galaxy, sometimes triggering further star formation in some regions and shutting it down in others. The surprising part from Webb is that our own galaxy center, which many people picture as old and settled, actually looks chemically young in this sense. The mix of alpha elements and suppressed iron, the presence of hot coronal gas, and the evidence for strong past feedback all say that the central parsec has had a recent, violent history. It's not a long-dead fossil core, it's a site of ongoing and relatively recent energetic processing. That has big implications. It means we should not think of Sagittarius A as having had one fixed personality over billions of years. Instead, its feeding rates, its outflow power, and the surrounding star formation have probably gone through phases, sometimes much more active than today, sometimes quieter. Webb has caught it in a relatively low state now, but with strong chemical and thermal clues that things were hotter and more intense not so long ago. And that naturally pushes you to zoom out again. If the chemistry and energy content of the central parsec have changed this much in just a few million years, what does that tell you about the bigger gravitational well the black hole sits in, the role of dark matter, and the overall evolution of the Milky Way in the context of what Webb is seeing about structure growth and dark matter on cosmic scales? How do you connect invisible dark matter on cosmic scales to the way gas and stars move right around Sagittarius A? And why does Webb force you to think about both at the same time? When you zoom all the way out, past the Milky Way, past our local group, Webb has been used to survey hundreds of thousands of distant galaxies using a technique called weak gravitational lensing. Light from background galaxies gets very slightly stretched and distorted as it passes through the gravity fields of foreground dark matter clumps. By measuring those tiny shape changes across something like 800,000 galaxies, astronomers can reconstruct where the dark matter is, how clumpy it is, and how fast big structures like galaxy clusters have grown over time. The picture that is emerging from these Webb surveys is that massive structures may have assembled a bit faster or in a slightly different way than some standard models had predicted. Dark matter halos seem to have pulled themselves together quickly in the early universe, providing deep gravitational wells earlier than expected. That is the cosmological backdrop, the big-scale skeleton of the universe that galaxies like the Milky Way sit inside. So why does that matter for a single black hole sitting 26,000 light-years away in the direction of Sagittarius? What does a dark matter map have to do with Sagittarius A? The Milky Way's central potential well, the overall gravity field that everything in the inner galaxy feels, is built from both the visible matter, like stars and gas, and the invisible dark matter. Sagittarius A is sitting right at the bottom of that combined well. The way gas flows in from large radii, the way orbits of stars tilt and precess, even the long-term stability of the central region, all depend on how the galaxy's dark matter halo and its stellar bulge formed and evolved. Webb's cosmological weak lensing results tighten the constraints on what a typical halo of the Milky Way's mass should look like, and how it should have assembled over billions of years. That, in turn, feeds into dynamical models of our own galaxy, including the bar, the bulge, and the central molecular zone. When you put those models together with what Webb directly sees in gas and dust near the center, you get a more complete sense of what kind of gravitational environment Sagittarius A has lived in, and how much gas it could have been supplied with over cosmic time. On smaller scales, right around the black hole, you already have one of the cleanest tests of gravity available, the stellar orbits. For years, observatories like the Very Large Telescope and Keck Observatory have tracked stars like S2, following their full orbits around Sagittarius A. Those orbits match the predictions of general relativity to within a few percent, including subtle effects like gravitational redshift near closest approach. That confirms that, at those scales, Einstein's theory is doing very well. Webb steps into this picture by refining the background mass distribution. The black hole is not the only source of gravity in the central parsec. There is also a dense cluster of stars and gas, and if you misestimate how much mass is in those components, you introduce systematic errors into the measured mass of Sagittarius A and into the precision of the relativity tests. With NIRCam and MIRI, Webb can map the light from stars and the emission from gas phases in the central region much more accurately, helping to pin down how much non-black hole mass is present and where it is located. That reduces the uncertainties in the models used to interpret the stellar orbits. So on one side, you have cosmological lensing, tightening the picture of how halos like ours form. On the other, you have local data around Sagittarius A, making our tests of gravity and mass in the central parsec cleaner. Put them together, and you get a sharper, more constrained story of how the Milky Way's potential well came to be, and what kind of environment the central black hole has grown up in. The surprising part for theorists is what happens when you combine all of this with the other things Webb is showing you. On cosmic scales, Webb's deep surveys are finding massive galaxy clusters and very heavy black holes earlier in the universe than many models have predicted. Those objects imply that structure formation and black hole growth were very efficient very early on. At the same time, when you look at our own galactic center, Webb shows a chemically young, energetically active core with recent massive star enrichment, strong feedback signatures, and complex gas phases, even though the current accretion state of Sagittarius A looks weak. If the universe is building big structures quickly, and if even a relatively quiet galaxy like the Milky Way has a central region that looks this fresh chemically and dynamically, then some of the standard assumptions about how dark matter drives structure growth, or how black holes grow and then shut themselves down, may need to be tweaked. Maybe dark matter halos clump a bit faster than expected. Maybe black holes go through more intense, short-lived growth spurts than our simple duty cycle models assume. Webb's local and distant views are both pushing in that direction, forcing simulations and theories to adjust. This leads to a crucial point. Sagittarius A might not be an average, middle-of-the-road supermassive black hole in every respect, especially not right now. Looking at the current X-ray and radio output, at the weak flares, and at the relatively low accretion rate, Sagittarius A today is a low luminosity state. Compared to bright quasars that can outshine their host galaxies, it is practically dim. But the chemical signatures in the central parsec, the evidence for strong past feedback, and the structure of the gas all hint that this is probably not its full story. In the past, given enough fuel from inflowing molecular gas and a different accretion mode, Sagittarius A could easily have been hundreds or thousands of times more luminous than it is now, more like a low-luminosity quasar than the quiet radio source we see today. Webb is catching the system in one frame of a very long movie, a frame where the black hole is relatively starved, but the scars of recent activity are still obvious in the gas and in the element ratios. That raises a high-stakes question for anyone trying to understand our own future and past. If Sagittarius A can switch between quiet and active phases, can we actually watch the early stages of those changes in real time by catching their flares and the echoes they send through the surrounding dust and gas? How do you turn a quiet-looking black hole into a clock and use its sudden bursts of light as a kind of time machine to probe the space just outside the event horizon? Sagittarius A is usually faint, but it is not steady. Every so often, it brightens in infrared and X-rays by factors of 10s to 100 for stretches of tens of minutes. These are flares, short bursts where the region close to the black hole suddenly becomes much more luminous. Webb can catch these with time series observations, where instead of taking one long exposure, it takes a rapid sequence of images or spectra, sampling the brightness every few seconds to a few minutes. When you line those up, you get a light curve, a record of how the brightness rises, peaks, and falls during the flare. Those light curves are not just pretty spikes. The timescales themselves tell you where in the gravity field the action is happening. The typical flare from Sagittarius A lasts on the order of tens of minutes. That is exactly the kind of timescale you expect for matter orbiting just a few Schwarzschild radii from a black hole with about 4.1 million solar masses. The orbital period close to the event horizon depends mainly on the black hole mass and fundamental constants. The more massive the black hole, the longer those innermost orbits take. For a stellar mass black hole, the timescales would be milliseconds to seconds. For Sagittarius A's mass, you naturally get tens of minutes. So when Webb sees an infrared flare ramp up and fade over maybe 30 to 90 minutes, you're not looking at something happening far out in the circumnuclear disk, tens of light years away. You're seeing a change in the flow of hot plasma right near the event horizon, where orbital speeds are a big fraction of the speed of light, and small changes in magnetic fields or density can cause big jumps in emission. The flare timescale is basically shouting, "This is coming from right at the edge." Once you have that, you can push the idea further. If the central region suddenly brightens, that pulse of radiation does not just vanish after we see the flare. It keeps going, and it can leave delayed signatures in the surrounding dust. Think about a clump of dust that sits a fraction of a light year away from the black hole, maybe a tenth of a light year, or about 1 trillion kilometers, roughly 620 billion miles. When the flare happens, photons travel outward at the speed of light. They hit that dust later than they hit us. They heat the grains, and the dust responds by glowing more brightly in the infrared. If you watch the surrounding region with Webb, you can look for small, delayed brightenings in specific dust structures, light echoes of the original flare. The delay time is directly related to the extra distance the light had to travel. A dust cloud 1 light year away will show an echo about 1 year after the flare. A cloud at half a light year will respond after about half a year, and so on. In simple terms, the delay in years is roughly equal to the distance in light years. That gives you a natural distance measuring tool. By timing the echoes in Webb data and mapping where they appear in the sky, you can reconstruct the three-dimensional layout of dust around Sagittarius A, not just its two-dimensional projection. So the flares let you probe the innermost regions, and the echoes let you map the surroundings. But to really understand the physics, you also need to know what kind of radiation mechanism is driving the flare itself. That is where Webb's spectral coverage becomes critical. During a flare, you can measure the emission from Sagittarius A at different infrared wavelengths. In the near infrared, you are sensitive to higher energy electrons and more compact regions. In the mid-infrared, you start to pick up cooler components and possibly reprocessed emission. If the flare spectrum is dominated by synchrotron radiation, that means hot electrons are spiraling around magnetic field lines at relativistic speeds and emitting across radio and infrared. If inverse Compton scattering is important, that means those hot electrons are upscattering lower energy photons to higher energies, which will show up in the X-rays. By comparing the near-infrared and mid-infrared brightness changes that Webb sees and matching them with X-ray data from observatories that catch the same flare, astronomers can figure out which process dominates. They can estimate electron temperatures right outside the event horizon, which can be trillions of degrees in normal temperature units, and they can constrain magnetic field strength and particle densities. In other words, multi-band flare observations are not just pretty graphs, they are direct probes of the plasma conditions in the inner accretion flow. When you cross-correlate Webb's flare light curves with X-ray light curves, you can even see if one band leads or lags the other. That timing offset tells you whether the X-rays are produced in the same region as the infrared emission, or whether they are generated later, after photons have been upscattered, or after energy has moved outward. That helps refine models of where different parts of the spectrum originate in the flow. All of this might sound very abstract, but if you translate it into concrete scales and speeds, it feels almost unreal. The structures responsible for these flares could be blobs or arcs of plasma comparable in size to the orbit of Mercury, which is about 58 million kilometers from the Sun, around 36 million miles. These blobs are orbiting at perhaps half the speed of light on orbits that loop around the black hole in tens of minutes. Magnetic fields are twisting and reconnecting. Particles are being accelerated to extreme energies. Some of the material spirals inward and crosses the event horizon, gone for good. Some of it is redirected into outflows that eventually slam into the gas and dust that Webb maps farther out. And you are seeing all of this with a telescope parked about 1.5 million kilometers from Earth, around the point of gravitational balance called L2, with its mirror and instruments chilled to tens of degrees above absolute zero so that it can pick up these faint infrared changes. You are tracking tiny brightness jumps from a region tens of millions of kilometers across, 26,000 light-years away, and then watching how those jumps rippled out into the surrounding medium over months to years. So flares and echoes together turn Sagittarius A into a kind of time machine. Short-term variability tells you about the immediate, near-horizon plasma physics. Longer-term echoes tell you about the geometry and composition of the dust and gas further out. Webb's role in this is to provide the infrared piece with high precision and good timing, while radio and X-ray telescopes fill in the lower and higher energy parts. Once you have that toolkit, it becomes natural to ask a bigger, tougher question. If you can study such subtle, low-luminosity flares this way in our own galactic center, what happens when you look back in time with Webb at the early universe, where supermassive black holes were already blazing as quasars less than 1 billion years after the Big Bang, and many of them were hundreds of times more massive than Sagittarius A? How do you explain a universe that builds black holes hundreds of millions of times the sun's mass in a few 100 million years, while your own galaxy's black hole is still only about 4 million solar masses after 13.8 billion years? Webb's deep surveys into the early universe have started turning up quasars in active galaxies that should not exist so early. You're seeing supermassive black holes less than 1 billion years after the Big Bang, with masses in the hundreds of millions to 1 billion times the sun, powering quasars that are 1 trillion times brighter than the sun. In some cases, Webb and other observatories are now finding rapidly growing black holes only 500 to 700 million years after the Big Bang. That growth is brutally fast. To get that big, that early, they either had to start from very massive seed black holes, or they had to feed at near maximal rates for a long time, or both. Now, put that next to Sagittarius A. Its mass is about 4.1 million solar masses, with current measurements tightly clustered around that value. For a black hole in a mature spiral galaxy that has had the full age of the universe to grow, that mass is on the low side. Plenty of galaxies host central black holes 10 or 100 times heavier. Even some of the early universe quasars Webb is seeing are already hundreds of times more massive than Sagittarius A, when the universe was less than 1/10 of its current age. So the obvious, uncomfortable question is, if baby galaxies could grow monsters so quickly, why is our own central black hole only at a few million solar masses today? Did it miss out on fuel? Did feedback choke its growth? Or has it been mostly idle for long periods? This is where Webb's detailed view of the Galactic Center actually matters for cosmology. By mapping the gas, the star formation, the recent supernova enrichment, and the current accretion state, Webb helps you reconstruct Sagittarius A's growth history and its duty cycle. Basically, how often it has been in a high accretion, quasar-like phase versus a low state like today. You already have hints from other wavelengths that Sagittarius A has not always been this quiet. In X-rays and gamma rays, instruments like Fermi and Rosetta have revealed enormous bubble structures extending tens of thousands of light years above and below the galactic plane, the so-called Fermi bubbles. These look like giant lobes of hot, energized gas and plasma, And one leading interpretation is that they are relics of past activity from the Galactic Center, possibly from an episode when Sagittarius A was accreting much more strongly and driving large-scale outflows. What Webb brings to this story is the fine-scale chemical map and structure of the central parsec and the inner few hundred light-years. If the black hole had a strong active phase a few million years ago, you would expect that to affect the gas, raising temperatures, changing ionization states, and mixing in products from short-lived massive stars that formed around the same time. That is exactly the chemically young, alpha element-enhanced, shock-filled environment Webb is now seeing near the core. The enrichment pattern Webb finds, biased towards elements made in core collapse supernovae, and the multi-phased heated gas are consistent with a recent period of intense star formation and strong feedback, likely linked to a more active Sagittarius A. So the next key question becomes, how much fuel has really been flowing toward the center, and at what rate could Sagittarius A have actually grown if it had eaten everything that came close? Clouds like Sagittarius B2 and structures in the circumnuclear disk are where you start to answer that question. Webb's measurements of gas masses, densities, and motions in these clouds let astronomers estimate inflow rates towards the central tens of light years. If you know a cloud's mass, say a few million solar masses for Sagittarius B2, and you have velocity fields showing materials streaming inward at tens of kilometers per second, you can work out how much mass per year could plausibly be delivered to the inner region. You express that as a fraction of a solar mass per year, or convert it to grams per second if you want a raw number. Then you compare that to what the black hole would need to grow significantly. To go from 4 million to, say, 40 million solar masses over the age of the galaxy, Sagittarius A would have needed an average growth rate of a few times 10 to the negative third solar masses per year, with some episodes likely much higher. The inflows you infer from Webb's data and from other observations of the central molecular zone tell you whether that kind of supply has been available. If the gas has been there, but the black hole has not grown accordingly, then feedback must have been very effective at throwing most of it back out. If the supply itself has been modest or intermittent, that also constrains the growth history. The circumnuclear disk is especially important here. Its clumpy molecular gas, moving on orbits at a few parsecs, is essentially the last large reservoir before gas either settles into an accretion flow or gets shredded and blown away. Webb's mid-infrared spectroscopy maps the conditions in that disk, where gas is dense enough to be a real feeder, where it's too hot or too ionized to be easily accreted, and where shocks and outflows are actively disturbing it. That lets theorists build more realistic feeding histories for Sagittarius A. All of this feeds back into a bigger modeling problem. Cosmological simulations now have to be tuned to match the heavy black holes Webb is seeing in the early universe, and the dark matter structure that weak lensing surveys are revealing. At the same time, those simulations have to produce galaxies like the Milky Way, with a central black hole that is relatively light for its age and environment, and with the Galactic Center that looks chemically and dynamically like what Webb observes. If you get the early growth right but overgrow black holes and Milky Way-like galaxies, you fail. If you keep Sagittarius A small but can't produce early billion solar mass quasars, you also fail. Our Galactic Center becomes a crucial calibration point for these models. And that sets up a provocative idea you need to hold on to as we go forward. Sagittarius A today might be an unusually quiet, starved phase, not representative of its long-term average. The evidence from chemical enrichment, from gas phases, and from large-scale structures like the Fermi bowls all point to periods when it was much more active. In those phases, its luminosity could be hundreds or thousands of times higher than it is now, approaching the low end of quasar power. So the tension is growing from both ends. Webb is telling you that some black holes in the early universe grew explosively fast, and it is telling you that even in a normal galaxy like the Milky Way, the central engine and surrounding stars have had a recent violent impact on their environment. The simple growth stories, where black holes just slowly track their host galaxies in a smooth way, are getting harder to defend. The next step is to stop thinking of Sagittarius A as just a point mass and start thinking of it as the driver of real galactic weather, winds, shocks, outflows, and turbulence on many scales, and ask how Webb actually sees those flows in motion, and how they regulate what gas ever gets close enough to be eaten. How do you call a place quiet when almost everything in it is being punched, pushed, and shredded by flows of gas moving faster than anything humans have ever built? When you put all the Webb data together, one pattern keeps showing up: outflows. Everywhere, on every scale. In Sagittarius C, you saw protostellar jets, long, narrow flows driven by newborn stars cutting through the cloud. In Sagittarius B2, you saw cavities carved out by clusters of massive stars and their winds. In the central parsec, you saw coronal gas and shock fronts at the interfaces around Sagittarius A. Webb is basically telling you, from a few astronomical units around a protostar up to light-year scales around the black hole, gas is not just falling in, it is also being pushed out. The clean way you see this is through Doppler-shifted emission lines in Webb spectra. In the mid-infrared and near-infrared, atomic and molecular lines that would sit at precise wavelengths in a static gas are shifted a little bit, blueward or redward, if the gas is moving toward or away from you. When you map those shifts across a region, you get a velocity field, a direct picture of where gas is streaming out, where it is rotating, and where it is being stirred. In the central molecular zone and near the Galactic Center, those line shifts are not small. Webb sees gas moving at tens to hundreds of kilometers per second. A speed of 100 kilometers per second is 360,000 kilometers per hour, about 220,000 miles per hour. For comparison, Voyager 1, the fastest spacecraft we have sent out of the solar system, cruises at around 17 kilometers per second, about 61,000 kilometers per hour, roughly 38,000 miles per hour. The gas flows Webb is tracing near Sagittarius A are several times faster than that. These are not gentle breezes, they are high-speed streams. On top of the bulk motion, the widths of the lines are broadened. If the gas were moving at one clean speed along each line of sight, the lines would be narrow. Instead, Webb sees line widths corresponding again to tens to hundreds of kilometers per second, meaning that within each pixel, gas is moving at a range of speeds in different directions. That line broadening is a signature of turbulence, so you have both ordered flows and chaotic stirring all encoded in the same spectra. So now you know the gas is moving fast and is turbulent, but you also want to know, is this gas confined, trapped by denser material, or is it actually escaping and venting out of the region? That's where pressure and density estimates come in. Webb's mid-infrared spectra contain lines from different gas phases: coronal, warm ionized, and molecular. The relative brightnesses and ratios of those lines are sensitive to temperature and density. From those, astronomers can infer pressures in each phase. If the hot coronal gas has a pressure comparable to or slightly above the surrounding warm ionized gas, and that in turn is balanced by the molecular gas, then the hot gas can be roughly confined, forming bubbles and pockets that push on their surroundings but do not just blow straight out. If the hot gas pressure strongly exceeds what the surrounding material can contain, you expect it to punch through and vent out of the central region, carrying energy and material with it. In the central parsec, Webb sees regions where hot coronal gas appears to be held in place by denser, cooler structures, and other regions where the geometry suggests that outflows are breaking out, feeding into larger-scale features. Combined with X-ray data and radio observations, you get a multi-layer picture: small bubbles, larger cavities, and on very big scales, things like the Fermi bubbles. It's a whole hierarchy of weather systems, running from small to huge. All of this ties back to one key idea: feedback regulating the black hole's diet. Gas that falls into the central tens of parsecs does not automatically end up inside the event horizon. To be accreted, gas needs to lose most of its angular momentum. Low angular momentum gas, material on orbits that bring it close in, is the most effective fuel. But that is exactly the gas that is easiest for outflows and winds to grab and throw away. When Sagittarius A has more fuel and the accretion rate ramps up, the inner accretion flow becomes more luminous and more powerful. That extra energy, in turn, drives stronger outflows and heats the inner region more. Those outflows remove or stir up the same low angular momentum gas that would have fed the black hole, reducing the inflow rate. Webb's data support this self-regulation picture. In the central parsec, where you might expect dense cold gas to sit and feed Sagittarius A efficiently, you instead see a dominance of warm ionized gas and signatures of shocks and hot interfaces. That says energy has already been injected into the gas, enough to change its phase and its structure. Combined with the sluggish star formation right at the center, it points to a system where feedback from both the black hole and massive stars keeps pushing the gas out of the most easily accreted configurations. When the feeding rate goes up, feedback kicks in and pushes it back down. So Sagittarius A is not just a passive drain at the bottom of the galaxy, quietly sucking in gas. It behaves more like a beating heart for the inner Milky Way, pumping energy and momentum into its surroundings. Protostellar jets in Sagittarius C, winds and supernova shocks in Sagittarius B2, outflows and hot gas in the circumnuclear disk and central cavity, they're all part of the same weather system, driven by gravity pulling matter in and feedback pushing it back out. Webb's role is that it finally resolves the arteries and veins of this system in the infrared. It maps where gas is flowing, how fast it is moving, what phase it is in, and how recently it has been heated or enriched. It links tiny scales near the event horizon, probed by flares and the Event Horizon Telescope, to large-scale structures in the central molecular zone and beyond. And here is the deeper point this sets up. If such violent weather can still support complex chemistry and rich organic molecules, like in Sagittarius B2, right under the influence of a supermassive black hole, what does that say about the availability of life's raw ingredients in the most extreme neighborhoods of our galaxy? How do you test how robust life's ingredients really are when you throw them into one of the harshest neighborhoods in the galaxy and see what survives? Down in Sagittarius B2, those dense clumps that Webb sees with MIRI are not just piles of cold gas, they're chemically loaded. Radio and millimeter telescopes already show that this cloud is packed with molecules, but Webb adds the mid-infrared view, where many complex organics reveal themselves through their vibration signatures. In plain terms, different bonds in a molecule absorb and re-emit infrared light at specific wavelengths when they stretch and bend, so the spectrum becomes a barcode. When you look at those barcodes in Sgr B2, you are seeing not just simple molecules like carbon monoxide or ammonia, but more complex carbon-based species, things with several atoms joined together, some of them similar to building blocks we associate with prebiotic chemistry. The important part here is the environment. This cloud sits a few hundred light-years from Sagittarius A in the central molecular zone, where radiation fields are stronger, shocks are more common, and turbulence is higher than in a calm spiral arm like the Sun's neighborhood. Yet these complex organics are still present. That tells you that with enough shielding in dense clumps, organic chemistry can survive and even thrive in conditions that are far from gentle. So if heavy radiation and shocks are not enough to erase these molecules, what exactly is protecting them? And how do we know what is really on those dust grains? In the mid-infrared, Webb doesn't just see emission from warm dust, it also sees absorption features where light from background sources passes through cold material. In shielded regions inside Sgr B2-like clumps, dust grains carry icy coatings made of water, carbon monoxide, carbon dioxide, and more exotic species. Each of these ices leaves a characteristic dip in the spectrum at certain wavelengths because the ice absorbs light there. By measuring how deep those dips are, astronomers can estimate column densities, basically how many molecules of a given type lie along each line of sight. So in a single spectrum, you can say along this narrow pencil beam through the cloud, there are this many water molecules on dust, this many carbon monoxide molecules, this many carbon dioxide molecules, and so on. When you repeat that for many lines of sight, you build up a map of where these ices are, how thick the coatings are, and how the chemistry changes from the outer, more exposed layers of the cloud to the inner, more shielded cores. The picture you get is that buried inside the violent central environment, there are pockets where grains carry rich, multi-layer ice mantles, loaded with oxygen, carbon, nitrogen, and more. That naturally leads to the tough question. Having the raw ingredients is one thing, but can you actually build planets in a place like this, especially as you move closer to Sagittarius A? Near the very center, in the central parsec, you already saw that the environment is extreme. Gas orbits at hundreds of kilometers per second. Tidal forces are strong. Turbulence and magnetic fields support clouds against collapse, and warm ionized gas fills much of the volume. In that zone, it is hard for stable, long-lived protoplanetary disks to survive. Any disk that tried to form very close in would be subject to strong tidal shear from the black hole and intense radiation from massive stars. That doesn't mean zero planets, but it makes the formation and long-term survival of planetary systems much less likely right next to Sagittarius A. Farther out, though, in regions like Sagittarius B2 and other dense clouds in the central molecular zone, conditions are different. There, you can still have dense cores collapsing to form stars, and around many of those young stars, disks of gas and dust will form as angular momentum redistributes. Those disks are built from the same material that Webb sees in the ice features and organic bands, meaning they inherit water, carbon-bearing molecules, nitrogen-bearing molecules, and other species straight from the parent cloud. Even if the turbulence is higher and the radiation field stronger than in the solar neighborhood, there are still shielded zones within disks where solid grains can grow, stick together, and eventually build planetesimals and planets. So you end up with a mixed answer. Very close to the black hole, the environment is probably too hostile for many calm, sun-like planetary systems. But in the broader central region, in Sgr B2 type clouds, tens to hundreds of light years out, protoplanetary disks can still form from chemically rich material. The planets that might emerge there would grow up under stronger radiation, more supernovae, and more dynamical disturbances, but the basic chemical starting kit is not missing. So that pushes you into a bigger discussion that has been going on for years, the idea of a galactic habitable zone. Classic models often drew a ring in the Milky Way, neither too close to the center nor too far out in the suburbs, where conditions for life were thought to be just right. Too close to the center and you get too much radiation, too many supernovae, and a strong tidal environment. Too far out and you don't have enough heavy elements to build lots of rocky planets. The sun sits somewhere in that mid-radius zone, and for a while it was tempting to think that was the main band where complex life could thrive. Webb complicates that clean picture. On one hand, its view of the galactic center confirms that radiation, turbulence, and shocks are indeed more intense there. On the other hand, the same observations show that central star-forming regions like Sagittarius B2 are chemically rich in organics and ices. The amount of raw material for complex chemistry may actually be higher per unit volume there than in the outer disk. So in the inner galaxy, you might have more food for prebiotic chemistry, but also more stress from the environment. That doesn't say life is likely or unlikely there, but it tells you the simple mid-radius story is too naive. The galaxy's habitable real estate might be more patchy, with safe pockets even in tough neighborhoods, and dead zones even in calm regions, depending on local conditions. And this leads to a powerful idea you can't ignore. If complex organic chemistry can not only exist, but stay active in the shadow of a supermassive black hole, inside a zone full of shocks, outflows, and high radiation, then the universe may be far more biologically fertile than our earlier conservative models assumed. You are looking at a region of only a few hundred light-years across, near the center of a single spiral galaxy, and it already contains dense clumps with water ice, carbon dioxide ice, carbon monoxide, and more complicated organics coating dust grains. These clumps feed into forming stars and disks. Scale that up across billions of galaxies, many of which have even more intense central starbursts, and you start to see why Webb's chemistry results are so important. They say that the building blocks for life are not limited to quiet, solar-like neighborhoods. They show up in violent, high-pressure, high-radiation places as well. So the next obvious step is to ask how long we can keep watching this story evolve. Webb's first look at the Galactic Center has already changed the way we think about black hole environments, star formation, and habitable zones. But what happens when we give it years of monitoring time, deeper exposures, and combine it with the next generation of giant ground-based telescopes and X-ray missions? Can we actually watch the central ecosystem change in real time, not just reconstruct its past? How do you judge what we know about the Galactic Center today when you already suspect that in 10 years, it's going to look embarrassingly crude compared to what's coming? Right now, everything you've heard about Webb and Sagittarius A is based on early cycle programs. These are the first passes designed to prove concepts, map key regions, and test observing strategies. The integrations are relatively short, the spectral maps are coarse compared to what the hardware can really do, and the flare monitoring has been limited in time. That's not a criticism, that's just how you start with a brand new telescope. In future observing cycles, teams can go deeper and much more targeted. Longer integrations with MIRI and NIRCam mean you can push to fainter structures, pick up weaker lines from rarer ions, and see smaller, cooler clumps of gas and dust that are invisible in first-look data. Finer spectral mapping with MIRI's medium-resolution spectrometer lets you shrink the spatial pixels, so instead of thousands of spectra across a central parsec, you can get tens of thousands, slicing the region more finely in both space and velocity. A dedicated campaign can sit on Sagittarius A for many hours or even repeated windows spread across months and years to build dense time series of flares, not just a handful of events. So the raw observing power is there, but the obvious next step is how do you combine Webb with the new instruments that are coming online on the ground and in space, so you're not just doing deeper versions of the same thing, but actually upgrading the whole picture. On the ground, facilities like the 30-meter telescope and the extremely large telescope will bring huge mirrors and advanced adaptive optics to the infrared. That means higher spatial resolution than Webb in some bands, but with the disadvantage of the Earth's atmosphere. In the X-ray band, next-generation missions will follow on from Chandra and XMM Newton with better spectral resolution and wider fields. Put together, you'll have extremely sharp infrared imaging and spectroscopy from the ground, high-energy coverage from space, and Webb providing deep, dust-piercing imaging and mid-infrared spectroscopy from its stable, cold orbit at L2. In that multi-wavelength network, Webb becomes the infrared anchor. It is the piece that always sees through the dust, that can tie the sharp but atmosphere-affected ground-based images to the more energetic but lower spatial resolution X-ray data. When Sagittarius A flares, you can catch it with X-rays, ground-based near-infrared, and Webb's near and mid-infrared at the same time. When you look at structures in the circumnuclear disk, you can check whether the fine features the ELT sees in the near IR line up with the gas phases that MIRI sees at longer wavelengths. The point isn't just more data, it's a tighter, more consistent picture of the whole system from radio up to X-ray. But even with all that, there's a basic technical point you still need to improve if you want to push the physics to the limit. How well do you actually know the distances, the dust extinction, and the detailed dynamics in the central region? Better extinction curves from NIRCam toward different parts of the central molecular zone will let you correct for dust more accurately. Right now, you have a good curve towards Sagittarius C and some other regions, but you can refine that across the field, mapping how dust properties change with position. That directly improves your ability to turn observed brightness into true luminosity, and true luminosity into mass for stars and emission measures for gas. On top of that, Webb spectroscopy can deliver spectroscopic parallaxes for central stars. By identifying certain types of stars whose intrinsic brightness is well known and measuring how bright they appear once you've corrected for dust, you can refine the distance to the galactic center and the distribution of stars around it. That feeds straight into the orbital solutions for stars like S2 and others. The more accurately you know the background stellar mass and the distance, the more cleanly you can test general relativity and pin down the precise mass of Sagittarius A. The goal is to shave down systematic errors until tight deviations from Einstein's predictions become either visible or very strongly constrained. Once you're doing that, you can start asking a different kind of question. Not just, what is the current state of the gas, but does that state itself change subtly over human timescale intervals? Repeat MIRI RMS observations of the central parsec, spaced out over years, can look for small changes in line strengths and ratios. If Sagittarius A occasionally has stronger flare episodes or slightly higher accretion rates that last longer than a single burst, those events will inject extra energy into the surrounding gas. That energy will reionize and reheat certain regions. Over a few years, you might see coronal line strengths creep up in some zones and fade in others, or see the balance between molecular and warm ionized gas shift in particular filaments. These changes will not be dramatic explosions in the images. They will be subtle shifts in spectra and velocities. But if you catch them, you're no longer just reconstructing past activity from static scars. You're actually tracking how new bursts from Sagittarius A propagate through the central parsec in near real astrophysical time. That's the difference between a single snapshot and the first few frames of a movie. All of this leads you to a clear escalation in how you should think about the next decade. The image of the Milky Way's core that you have today, from early Webb cycles and existing X-ray and radio data, is already far beyond what we had before 2020. But compared to what a coordinated Webb plus ELT plus TMT plus next-gen X-ray and radio program can do, it will look primitive. Today's picture is like the first detailed photograph. The next decade is about turning that into a time-resolved, multi-phase movie of a supermassive black hole ecosystem. In that movie, you'll watch gas flow in from giant clouds like Sagittarius B2, see how it gets shredded and heated in the circumnuclear disk, follow flares and outflows from Sagittarius A as they slam into nearby gas, and track how all of this changes the chemistry and the star formation in the core. Webb is the instrument that started this shift by resolving the dust-hidden structures and the gas phases for the first time in this much detail. The next decade will be about using that foundation to watch the system evolve, not just exist. And once you've seen all that chain from enormous molecular clouds down to the last few light minutes around the event horizon, there's one final step. You have to step back and ask what this does to your picture of the Milky Way as a whole, and what it means for our place inside this system that suddenly looks much more alive and much more dangerous than the calm band of stars you see in the night sky suggests. How much has your picture of the Milky Way changed now that the thing at its center is not just a mysterious radio blip, but a whole ecosystem we can actually map? A few decades ago, Sagittarius A was basically a compact radio source. We knew something dense and heavy was there because of how nearby stars moved, but it was a point on a radio map, nothing more. Then the Event Horizon Telescope pushed into the smallest scales and gave you a direct image of the black hole's shadow, a ring about 51.8 million kilometers across, roughly 32 million miles, tracing where light orbits before falling in or escaping. That was the confirmation. Yes, there really is a 4 million solar mass black hole sitting at the galactic center. Webb didn't try to redo that close-up. Instead, it stepped back and lit up everything around it. With NIRCam and MIRI, it turned the central few hundred light-years from a dusty blur into a structured map of molecular clouds, warm ionized gas, coronal gas, and star-forming regions. It measured gas temperatures, densities, and velocities. It pulled out chemical abundances, showing which elements are enhanced and which are suppressed. It mapped where star formation is raging and where it stalls. It basically transformed Sagittarius A from a black hole we know is there into a full environment with a history that you can describe in detail. So what exactly did that new view break in terms of simple stories you might have believed before? First, the central parsec turned out to be chemically young, not old and settled. The strong lines from alpha elements like neon and sulfur compared to weak iron lines point to recent core collapse supernovae from massive stars, not just slow enrichment from ancient low-mass stars. That tells you the core has gone through a recent burst of massive star formation and violent feedback. Second, clouds like Sagittarius B2 are ridiculously efficient at making stars. Sagittarius B2 only has about 10% of the total gas in the central region, but it produces roughly half of the ongoing star formation there. That's way beyond the simple more gas, more stars expectation. Webb's view of dense clumps, warm dust, and embedded clusters shows you a star factory running near maximum output. Third, right next to the black hole, where you might think star formation should be easiest because the gas is concentrated, it's actually sluggish. Inside a few light years of Sagittarius A, Webb sees plenty of gas and dust, but most of it is warm, ionized, and turbulent. Tidal forces from the black hole, strong magnetic fields, and feedback from earlier massive stars all combine to make it hard for new stars to form. The gas is there, but the conditions are hostile to collapse. Fourth, at the smallest scales, the Event Horizon Telescope's polarized images show strong, organized magnetic fields wrapped around the event horizon. That rules out the simplest picture of a chaotic, unstructured flow. Those fields likely shape the outflows and weak jets that Webb then sees the results of in the central parsec as shocks, coronal gas, and carved cavities. Each of these points overrides a neat old intuition that the very center should be chemically ancient, that gas density alone sets star formation rates, that conditions always get better for star formation as you move inward, and that black hole fields are messy rather than ordered. Webb, together with other observatories, shows those assumptions just don't hold in detail. All of that feeds into how you see the Milky Way itself. It's easy to picture our galaxy as a mostly quiet, aging spiral, with a thin disk, some calm spiral arms, and a central bulge where not much changes anymore. The Sun sits in a suburb, orbiting at about 26,000 light-years from the center, and from here, the Milky Way looks like a static band of light across the sky. But when you add Webb's view, the inner region stops looking like a gentle bulge and starts looking like a live engine. In the central few hundred light-years, massive molecular clouds like Sgr B2 and Sagittarius C are forming stars hard and fast. Massive stars are pumping out ultraviolet radiation in winds, then exploding as supernovae. The gas is multi-phase, with cold molecular clumps, warm ionized filaments, and hot coronal pockets all interacting. Outflows and shocks are launching material outward and inward. The central parsec shows the chemical fingerprints of recent violence, and even in its current faint state, Sagittarius A is launching flows and flares that Webb can catch in infrared. So instead of a static old bulge plus sleepy black hole, you end up with a core that is still shaping the galaxy today. It's regulating star formation near the center, stirring and enriching gas that will move out into other regions, and occasionally lighting up in flares that send pulses of energy through surrounding dust and gas. The core is not just a historical curiosity, it's a current driver of galactic evolution. And this all loops back to you, sitting on a small planet around the fairly ordinary star in one of the Milky Way's spiral arms. Every clear night, if you look toward the constellation Sagittarius, you're looking into the direction of this entire system. Along that line of sight, past the foreground stars you can see with your eyes, lies a black hole about 4.1 million times the mass of the Sun, compressed into a region smaller than our solar system. Around it, in the central few light-years, gas is orbiting at hundreds of kilometers per second, hundreds of thousands of kilometers per hour. Shock fronts move through that gas at tens to hundreds of kilometers per second, or tens to hundreds of thousands of miles per hour. Farther out, in clouds like Sgr B2, millions of solar masses of gas are collapsing into new stars, while complex organic molecules and ices coat dust grains in shielded clumps. Jets from newborn stars in Sagittarius C stretch for over a parsec, more than 3.26 light-years, roughly 206,000 astronomical units, cutting through their parent clouds. Supernovae have gone off in the central parsec, injecting on the order of 10 to the 44 joules of energy each into the environment. And all of this is bound together by the gravity of the galaxy and the dark matter halo that Webb has helped map on the largest scales. Your solar system is orbiting inside that gravitational story, taking about 200 to 250 million years to make one lap around the Milky Way. You're not outside observers looking at someone else's galaxy. You're inside this one, in a system whose core has been far more active and far more complex than the quiet band of light in the sky suggests. Webb's look at Sagittarius A doesn't just give you prettier images. It rewrites your place in the galaxy as part of a dynamic, evolving structure where a central black hole, massive molecular clouds, and multi-phase gas all interact over millions of years. You are living in the outskirts of a galaxy whose heart is still beating, and for the first time, we have a telescope that can show you the arteries, the veins, and the shocks in that heartbeat in real physical detail. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.